All right, even though I'm not there, don't be this guy. So let's get started. What are we talking about today? This is the part where you freak out because you see the word geometry, but don't, because this is going to be cool geometry, not that geometry. So what are we going to be doing today? We're going to learn how we take that Lewis dot structure that you've been working on and turn it into a three-dimensional structure. What does it actually look like at the atomic level? Now, what's going to affect what a molecule looks like is the electrons. This is why I've been telling you, make sure you put all the dots there, take account of everything, because now it is all coming back and getting put together now. So we're going to learn today how to take our Lewis dot structure and make a 3D model of it. Now it's going to be a little bit difficult because you're going to have to draw 3D structures down, and it's difficult to draw a three-dimensional structure two-dimensionally. But today we're going to work on trying to learn what that structure looks like, and then next class you're going to actually build it. Dramatic pause. All right, so pardon my dog. So what are we learning about today? Making a three-dimensional structure. How we make it is actually, it falls under the VSEPR theory. And VSEPR theory is all about this valence shell electron pair repulsion theory. You just got to remember VSEPR. And the main thing you've got to remember about VSEPR is why a molecule looks the way it does is this is for covalent compounds only. The reason why it looks the way it does is the electrons. How the electrons react. Because remember, electrons are negatively charged. And because they're all the same charge, they're going to repel each other. They don't want to be next to each other. They can't be next to each other because of that magnetic negative force that's going to repel them. And that's going to affect how an atom looks. So again, here's some examples of the different types of shapes we're going to be seeing molecules make. You do not need to memorize these names, but you need to be able to read a table. So you picked up that other handout that was that table looking thing. You want to have that out, because what we're going to be doing today is basically learning how to use that table, which I will give you on the test, but how to use it, that's where it's up to you. So let's go over how we use this table. We'll start with this example, beryllium fluoride. You can see I've done the Lewis dot structure for you here. And because of all of these electrons, well, they want to be as far away from each other as they can. And that's where that's the whole VSEPR theory is. They're going to get as far apart from each other as they can. Now, the VSEPR theory, the VSEPR table, how people write it up can be one of two ways. The old school way, it is the ABE table. The new school way, it is the AXE table. The one I gave you, I believe, is the AXE table. So that's what we're going to learn how to use. So you want to write this down. This is what we call our general formula. This is what we have to create so we know how to read the table. And the A stands for the central atom. So basically, we're going to take a formula, then do a Lewis dot to it, then, there we go, then change it into an AXE formula. So the A just represents the central atom, which you determine by using electronegativity. The X represents how many elements are bonded to the central atom. So this tells me, in this example, that there are 2 elements bonded to that central atom. The E tells me how many pairs of electrons are bonded on the central atom but not bonded to another element. So for this example, there are 2 electron pairs also bonded to the central atom. But this is your general formula. This could be AXE, or if you're old school, it might be ABE, and again, B standing for bonds. So let's do an example because you're probably kind of confused, and you're going to see how easy this is. So take this table out, have it ready, and let's do water. So we know water is dihydrogen monoxide. Let's draw it out. I know we have H bonded to O, bonded to H, dot, 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 dot. So let's write out, so there's our first step. Now that we have that, let's write out our AX formula. So we know oxygen's the central atom, and it's A. Next, we need to know how many atoms are bonded to this central atom. And you can see there are 2. There's 1, there's 2, bonded to the central atom. Then we need to know how many electron pairs are on that central atom. And we see there's 1 and 2. So there is our AX formula. Now look at that table. Oops. You want to look for, what was it? AX2, E2. So AX2, nope, no E, AX2, nope, nope, no E2, nope, 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 nope. Ah, there it is. AX2, E2. And that tells us everything 3D-wise about our water molecule. So how I would draw this is my central atom. There's my O. Then I've got what? My 2 H's, sorry about that, H's. And then I've got my 2 electron pairs, which they put like this. Now hold on, let me see if I can erase that one icky line. There we go. There we go. So this right here is how I would draw water to represent it 3-dimensionally on paper. Now, if I were to give you the little model set to build it, it's going to look more like this. But what you want to get out of this is, again, those electrons, they take up space. So that's why this guy is pushed down, why the hydrogens are pushed down, and it's got kind of that bent structure. Oh, look at that. It's got a bent structure because we had to take those electrons into account. Now, all right, so we have our formula. We've got the picture to help guide us how to draw that structure, that 3-dimensional structure on paper. It'll tell you the bonded atoms and the lone pairs. Okay, you already calculated that. It tells you its molecular shape. There it is, it's bent. This electron geometry, just kind of scribble that out. We don't really use it here in Chem Honors. You'll use it in AP Chem if you take the class, not so much here. Same thing with the hybridization. We don't really use that here, that's more AP Chem, but we do care about the bond angle, which, oh, look at this whole, all of these guys have a bond angle of 109.5. So what that's telling you is this right here is 109.5. So is this, so is this, so is this. All of those are 109.5. Now don't forget, we're looking at this 3-dimensionally. So we've got our x-axis, our y-axis, and also our z. And we're trying to take that 3-dimensional structure and draw it on paper. which is why we draw it like this, as opposed to just a plain old Lewis dot. That's a lot more work, so we don't always draw the VSEPR theory, but in order to, the VSEPR notation, but in order to draw this VSEPR structure, we need to know the Lewis dot structure. So if you don't know how to do the Lewis dot structure, this is going to be very difficult. So you've got to work on that. All right, so looking at having that by your side, you try this one, beryllium difluoride. So the first thing you need to do is write its AX notation. Give you a second. So did you do AX2? You've got 2 fluorines bonded to it. Did you take that into account? Okay, keep going. If you look, there are no electron pairs. So what do you write here? Nothing. It is just AX2. So take a look at your structure, your table here, and find AX2. Hopefully you found it right there at the top. There's all the information you need to know about it. Again, this line we don't care about, that line we don't care about. Now looking at the VSEPR theory, how would you draw this to be a VSEPR structure? Hopefully you put B in the middle. And your F's off to the side. There you go. That's your VSEPR. Notice there's no electrons here on your F's. Because for VSEPR, we don't care about those electrons on the outer guys. We only care about the electrons on the central atom because they're going to affect what that element looks like. So Lewis dot, we care about everything. VSEPR, it's all about the central atom. All right, so again, you can kind of see when you see a picture like this, what this is telling you is all of those angles are 120. We just write it once because why write it multiple times if it's the same? So this one here, all the angles are 109.5. Don't forget this picture here because you're trying to draw what it looks like. Structurally, we're gonna add little triangles, we're gonna add dotted lines. You don't need to know which one's which, but one of them's gonna represent X, Y, and one represents Z. That's what that's all about. All right, so, pardon me, again, VSEPR, we care about those lone pair electrons on the central atom. And they take up space, just as much space as the bonding pairs do. So we have to take those into account, which is why you have to do the Lewis dot structure first, then the VSEPR structure. Because those lone pair electrons take up space, they're going to affect the bond angles. So you always have to do Lewis dot first, then VSEPR second, because you've got to find out if that central atom has any lone pairs of electrons. Now, if something has a double bond, like, carbon dioxide here, or if it's got a triple bond, when it comes to VSEPR, we don't care. This carbon is bonded to 2 elements, and there is nothing, no lone pair of electrons in that central atom, so we don't take it into account. So whether it's a double bond or a single bond, when it comes to going from Lewis dot to VSEPR, nobody cares. We care for the Lewis dot structure, but not for the VSEPR structure, because it's not, the number of bonds is not going to affect the electrons on the central. Well, it's not going to, it is going to affect because you'll have less, but it's not going to affect the shape. All right, now, going back to that worksheet where we had to draw the structure and then use the structure to determine if it was polar or not polar, that's where this ties in. Now that we have that structure, we can really determine if something is polar or nonpolar. Again, all of this is for covalent. Now the default, we assume everything is polar unless one of these two things happen. So in order for something to be nonpolar, we have to look at those electronegativity values, and they have to be equal. So if we've got oxygen bonded to oxygen, we know those electronegativity values, sorry, of course, only when I do this does my dog want to play. We've got the exact same electronegativity values, so it's going to be 0 when we subtract the two. So if it's the exact same atom, it's going to be nonpolar because those differences are equal. Now, we know from that table that there's a range. If it's not exactly equal, how do we know if it's leaning towards the nonpolar or leaning towards the polar? And that's when we have to draw that 3D structure and then add those arrows to it that we drew before. So let's do an example. So OF2. First, we're going to start off drawing the Lewis dot structure, because we need to do that in order to go to VSEPR. Oh, sorry about that. Let's delete that. There we go. We don't need that one. We don't need that one. We'll go back to that one. All right. Now that we have that, now we can go to the act structure. So go ahead and, what do you think the act structure is by looking at that? You've got your central atom, your O. Let's see how many atoms are bonded to it. We've got 2. Are there any lone pairs of electrons on the central atom? We've got 2. So now we're going to draw out our Lewis dot structure. Let's see, we have AX2E2. There it is, AX2E2. So let's draw that out. So we've got sorry about that. O in the center. We have an F here. We have an F here. I don't need to draw those dots, so I'm not going to because this is VSEPR. We've got our electrons here and our electrons there. Now we need to add the electronegativity values. So let's take a look at that. For oxygen, it's 3.5. For fluorine, it's 4. So oxygen is 3.5. Fluorine is 4. Whew, if I could write, that would be better. So now if we look, the electrons are going to be hanging out over that way. And if this were a tug of war, would oxygen move? So if this was a tug of war, would oxygen move? And hopefully you're seeing, hey, yeah, they're kind of pulling that way, but I think oxygen is going to move that way. Because even though these are electrons, they don't have any electronegativity values, so everybody's leaning towards that way. So if this is a tug of war and that central atom's going to move, then we say it's polar. If that central atom did not move, we would say it is nonpolar. And this one, for us right now, it's going to be the difficult one because it's kind of subjective on how does it look to you, but we got to get started somewhere. So this is where we're going to start. All right, now you try this one. Do Lewis dot first, then change it to X, then draw it out. Excuse me. Give you a hint, carbon is your central atom. All right, go ahead and check yourself. Did you draw it correctly? If not, circle it, highlight it so you can look at it later and try and figure out where you went wrong. Now, change this to X notation. So how many atoms are bonded to that central carbon? We've got oxygen that's double bonded. We don't care that it's doubled, it's bonded. There's one. We've got a hydrogen and another hydrogen. So it's AX3. Are there any lone pair of electrons there? Nope. So that's it. It is just AX3. So go ahead and look at your chart and look for AX3. And there it is. So let's redraw it using our VSEPR drawings. Just change the A's to the elements that apply. Oops, I didn't put the right elements there. Silly me. There we go. Let's try that again. So there is our VSEPR structure. Now hopefully on your copy you can see the little triangle to represent like the X plane, the dashed lines to represent the Y plane, and just the plain old line to represent the Z plane, or whatever planes you want to pick. It doesn't really matter, but they're to represent, hey, one sticking in front, one sticking behind. Now that we have that, let's look at our electronegativities. Carbon is 2.5. Hydrogen is 2.1. And oxygen is 3.5. So where are those electrons going to hang out? Draw your arrows. Where are they going? Did you do the hydrogens? So the hydrogen electrons are going to hang out on the carbon. Now let's do carbon compared to oxygen. If this were a tug of war, would carbon move? If you look at it, you've got two of these guys going this way and pulling that way. So hopefully you can visualize this carbon atom is going to move this way. And because it's moving, it's polar. So to determine if something's really polar or nonpolar using VSEPR, you're going to need this table, which I will give you on a test or a quiz. You just need to know how to use it. You're going to need to know, you need the electronegativity values. You don't need to memorize them. I will give you this table on a test or a quiz. You need to know how to use them. So today was basically how to use these tools that I gave you. And hopefully we'll be able to do that. So that's it. Let's give it a try and see if we can.